All right, can you see the slides now? Okay, good. Okay, let's move on. We've gone through some introduction on CMOS. So all right. So again, CMOS is a complementary metal oxide semiconductor. So it's a combination of PMOS and NMOS. So when we say it's PMOS or NMOS, so the device is actually defined by the type of channel in the MOSFET. So PMOS or NMOS is actually MOSFET. So it's defined by the channel in the MOSFET. So if you're talking about N channel between source and drain, so that means it's an NMOS. So if you're talking about a P channel between your source and drain, then it's a PMOS. To be able to get a CMOS or complementary metal oxide, we have to combine both PMOS and NMOS in the circuits. Okay. Right. PMOS and NMOS or CMOS is used in integrated circuits, chips, microprocessors, microcontrollers, memory chips, and other logic devices as well, and also being used in analog devices such as what's written on the slide. CMOS sensors, data converters, RF CMOS transceivers, and many others. Okay, so those are some introduction to CMOS. And MOSFET was invented in Bell Labs back in 1959 by these two scientists, Atala, an Egyptian guy, and Daewon, a Korean. So back then in 1959, 1960s, the gate length or the gate dimension of the MOS P and N are in the region of 20 micron. We're in the region of 20 micron and 10 micron. So that means it was so huge back then, right? On the device. Okay, last time I've drawn this structure to explain to you about the gate dimension. So source on the left, drain on the right. Gate here, source, drain, and oxide there. Gate oxide. So the gate dimension is defined by the width of the gate. So it's also called a technology node if you're talking about manufacturing in industry now, right? So when it says technology node, so that means it's referring to the gate width of the device. So back then it was 20 micron and 10 micron. So some other history on CMOS. It was first invented by these two guys at Fairchild in 1963, and then they published a research paper on this somewhere in 1963 as well. And then they even filed a patent, a US patent for the first CMOS circuitry back in 1963, and it was granted 4 years ago. 4 years after that, right, in 1967. And you can read the rest of the history of CMOS, where after the patent was granted, there are companies taking up the technology for the fabrication, so on and so forth. Okay, this is the basic CMOS configuration. So we have learned that CMOS is a combination of PMOS and NMOS. So we have learned already about the basic structure of a PMOS or NMOS, N-channel transistor, N-channel MOS or P-channel MOS, right? So the left hand side here is NMOS, where you can see the N-type, the N-channel is here, connected, connecting source and drain. So the substrate is P-type, so the channel is N-type, so therefore it's NMOS. So on the other side, within the same wafer, So just adjacent to the NMOS, there is a PMOS. So you can have a look here, because the wafer is p-type, so to be able to set the substrate polarity, it doesn't have to be a completely new substrate, but instead you can actually diffuse a well. This is a well just behaving like a substrate. Nanti kita akan belajar dalam 487 semiconductor fabrication, how do we actually do this well on the opposite type wafer. So for example, in this case, kalau your wafer is p-type, so how do you do the n well so that the whole structures in the n well behaving just like they sit on n substrate, right? But there is actually prepared by fabrication process. So in this case, for the NMOS, for the PMOS, so the well is prepared so that the whole structure sit in N structure. So then we prepare a source drain of P plus, and then therefore the channel will be P type. Right, the channel will be P, therefore it's called PMOS. So therefore it's called PMOS. Okay, so PMOS and NMOS as a CMOS gate structure. Okay, these two structures can also be represented by this symbol. We've learned this one in MOSFET, but we've learned them separately. Either it's p-type or n-type, but this is where they are combined in a CMOS circuit, so they are no longer separated. Okay, so what you can see here, VDD is the supply voltage, VSS is the ground, is the source voltage. So it's going positive this way. So if you look at this symbol, which one is the PMOS and which one is the NMOS? Now you tell me which one is the PMOS and which one is the NMOS. Atas PMOS ke NMOS? The top one, is it PMOS or NMOS? Look at the arrow. Which one? Atas PMOS. Okay, atas PMOS. Kenapa atas PMOS? Arrows going out, right? So atas is PMOS. So the top one is PMOS, the bottom one is NMOS. Okay, the top is PMOS and the bottom one is NMOS, and they share the same input voltage and they produce one output voltage. So one input, one output. Right, so we'll see how they work in the next page. So before that, let's move on. Let's look at this right table summary. It's on MOSFET scaling. So back then in 1959, 1960s, the gate size, the gate width, okay, the gate width was around 10 micron, 20 micron. So you can see here, as the time goes on, right, from the 70s up to now, so the industry has gone down to really small gate width. So up to now we have around 5 nanometer by IBM, and TSMC is planning for 5 and 3, will be in the production soon. So it's gone down from tens of microns to only a couple of nanometers, right? So when I joined Silterra back then in 2003, Silterra was doing 250 and 180 nanometer. Okay, so when I left Silterra, Silterra just started 90 nanometer. So now if you talk about international context, then we have 5 nanometer in place, 7 nanometer in place already. But if you talk about Malaysia's context, the best we can do is somewhere 90 or 80 nanometers. So that can be done by Silterra. Okay, if you talk about Infineon, then they are doing some other, they are not after lower nodes technology, because the application that they use do not need to use chips with small gate length, so therefore they are now working with 350, a couple microns technology. In fact, some of the technologies are with 1 micron gate length. Okay, so tak semestinya kalau kita go for lower technology nodes, not necessarily all companies will do, because it depends on what their customer wants. So if their applications need chips with lower gate length, then they have to go for that, or else they don't have to. Okay, they don't have to. So in the case of Infineon, they don't have to. Okay. All right. This is also called technology node or process node. Okay. So the term used in industry is called technology node. Okay. Beside in the industry, if you join a semiconductor wafer fab like Silterra, Mimos, Global Foundries, and some others, they also call this gate width as critical dimension. Critical dimension. Critical dimension, or CD. So this is actually the same thing. Gate length, gate width, or CD. Nanti kita akan belajar in 487 when we do the fabrication. When after you finish doing the process of fabricating the gate, you have to make sure that the gate is of the correct specification. For example, if you do lithography and etching processes, you have to make sure that, for example, if your gate is 130 nanometers, so you have to make sure that the CD is 130 nanometers plus minus, I don't know, maybe 5 nanometer, the variation that it can handle, right? Or else it will produce different device performance. So, and this the measurement is called CD in wafer fab. Okay, critical dimension. All right, next, how does a CMOS work? CMOS is also called an inverter, okay, or a NOT logic gate. Masih ingat ke apa a NOT logic gate? Can you still recall a NOT logic gate from your digital electronics? What is a NOT logic gate? Anyone can share? What is a NOT logic gate? How do you tell it's a NOT logic gate? Zero has one output, one has zero output. Yeah, correct. Good. So if you put zero input, you're going to have one output. If you input one, then you're going to have zero as output. So it's going to flip the output. Okay. So maksudnya kalau your signal is on, then your output is off. If your input is off, then your output is on. Okay, so that is a NOT gate. So let's look at this truth table. Truth table ni ada belajar dalam digital kan? Yes. Okay. Right. Okay. So kita tengok kat sini ya. If you look at this CMOS, so it's a combination of PMOS and NMOS. So the top one here is a PMOS. The bottom here is NMOS. Okay. So for a PMOS, sebelum kita tengok circuit ni, PMOS, NMOS. PMOS punya basic operation is that if you input one, the output is going to be flipped. If you input zero, the output is going to be flipped as well. So that means for a PMOS, if you input one, you're going to have zero output. For a PMOS alone, right? Not in combination yet. For an NMOS, if you input one, you're going to have one. If you input zero, you're going to have zero. So that's the basic operation of PMOS and NMOS respectively, not in combination. Sekarang kita tengok what's going to happen if they are combined. Right, so let's look at the truth table here. Let's look at the first case. If you input zero, so that means you do zero here. So apa akan jadi? So one end is connected to VDD, high voltage, positive voltage. One end is connected to ground, or ground, zero. So apa jadi? If you input 0, they share the same input, by the way. So transistor 1 will be off. Transistor 1 is NMOS. Kenapa dia off? Because if you input 0 for an NMOS, the output will be 0, right? So the transistor will be in off state. So 0 means 0. So therefore NMOS will be 0. So it will be off, no operation. So on the other hand, let me prove your friend here. On the other hand, for a PMOS, if you input 0, it's going to be flipped to 1. So therefore transistor 2 will be on. When transistor 2 will be on, the VDD will be taken as your output. So the output will be equal to VDD. Will be 1 as well. So therefore in the truth table we have, for a 0 input, we're going to have a V out of 1, because V out is equals to VDD, and that's equal to the high voltage. So if it's not grounded, then it's a 1. Okay, it's a 1. So that's for the first case. So for the second case, if you input a 1, to this CMOS, so apa akan jadi? For a T1 transistor 1 output equals to 1 input, because it won't be flipped. So transistor 1 will be on, transistor 2 will be off. So T2 PMOS will be off because the output is flipped. So T1 is on, T2 is off, so VDD is disconnected from the circuit. So therefore the ground output, or 0, will be taken. 0 will be taken as the output. So VDD will be equal to, V out will be equal to 0. So therefore you have 0 output. So that's how it works. Okay, is it clear? Quite straightforward, right? Is it okay? The bottom rule that you have to understand is that a PMOS, it will flip the output. NMOS, it will follow the input. Right? Sorry, PMOS, it will flip the input. NMOS, it will follow the input. So for a PMOS, if you input 1, you're going to have 0 as the output. NMOS, if you input 1, you're going to have 1 as your output. Okay? So then you can just do on-off thing, and then you're going to have your output voltage. A slightly more complicated will be a CMOS NAND gate. Apa maksud NAND gate? It's a logic circuit NAND. What is NAND? Is it not AND? Nanti you try work this out, okay? Try work this out. How does it work? Not AND, right? Not AND. You AND A and B, and then you not, right? You bracket AND first, A and B, then not. Then you're gonna have NAND. So I'm not going to go through the truth table. You figure out yourself. Look at this. The right hand side is the physical layout of a typical design. Ni design yang simple lah. Sebab dia nampak very simple. It's actually much more complicated than this if you're talking about billions of transistors. So some areas, kerja ni actually is done by a design engineer. So kalau you join Intel, for example, ataupun Altera kat Malaysia, what else? Kat Malaysia ada few design house. Design house ni macam, ataupun manufacturer which also has a design department, just like Altera in Penang, Intel in Penang and Kulim. So they do have design engineering posts. So if you join design engineer, if you are a design engineer, then you're going to have to design this. Metal kat sini, tengok ni metal. Then whereas poly ni we're going to learn this one a bit later on in 487. Tapi this one is just a brief introduction to you on the circuit. This one is actually a top view, okay? Top view. Kalau you tengok satu circuit CMOS tu, dia punya metal kat mana, dia punya well kat mana, you diffuse source, gate and all those stuff. contacts. So all these black dots are contacts. And diffusion, this one is where your wafer will be N type, ni merah. So P diffusion kuning, this where your wafer will be P type. Well, so some regions are in the well, so all those stuff, right? So this is a basic design of a NAND circuit. So kalau kita, this is a zoom in untuk a simple circuit. If you go out, if you zoom out, then you're gonna see billions of this design. So ni antara kerja yang dibuat oleh design engineer. So kalau you know, if you get to do this job, then your day in and day out is sitting in front of a desktop or laptop doing the design of this circuit. So you can buatlah mana biru, mana hijau, mana kuning, and then the moment the design is completed, you're gonna pass your design to mask maker. Kita dah belajar kan mask a bit. Did I teach you about mask or not yet? Maybe mask untuk lithography process, that will be next session. Sorry. So mask tu kita nak print circuit. So we're going to learn later on that to be able to print your source, your drain, your gate, your oxide, your well, your whatever, we're going to have to do a process which is called a lithography. Ni introduction ya, photolithography. I was a litho engineer last time in Soltera. It's called lithography process, photolithography. Lithography here is printing process. Lithography printing macam stencil process, but we are printing the circuit, we are printing all the transistors or sensors or whatever using light. Photolithography, printing by light, printing using light. So we're going to use lasers and UVs and I line and G line and many more laser sources to be able to print all the small circuits like 10 nanometers, 7 nanometers. Okay, so it's not an easy process. So tapi before you do the printing, the design is going to be done by the design engineer. Dia akan buat design ni, then you akan come up with a stencil macam nak print baju kan. Just imagine as a print baju punya process. Tapi baju kalau kita print, let's say you want to print this, you want to print these stars and Australia and whatever, so you're gonna have to have a simple stencil punya mask lah. So this very same thing, you're gonna need to print your circuit, just like here, metal, diffuse, a contact, whatever. It's gonna be in terms of your metal mask or chrome mask. Okay, so design engineer can prepare the design, and then it's gonna be passed to wafer fab, macam Sultera ke Infineon ke. In fact, Intel has its own wafer fab, but not in Malaysia. So they're gonna do all the wafer fabrication process from a blanket wafer, from a bare wafer yang silicon kita tengok kan, silicon bulat kosong, until it's full of billions of transistors yang ada thousands or millions of chips. So it's going to be done by the fab. But beforehand, before the fab can do the job, the very first job will be done by the design engineer. So this is a very simple representation of what they actually do. Okay. So hari-hari you akan tengok color biru, hijau, merah every day, day in day out. You're going to sit in front of a PC and do your design stuff. So that's the job of a design engineer. Alright, so let's move on to CMOS high K dielectric. Okay, what is this stuff? I've uploaded videos to you to watch. Please watch them if you haven't watched. So we have discussed about CMOS scaling process kan. Scaling means reducing the gate width, gate width, or maybe CD. Kita nak reduce the CD from 100 nanos to, I don't know, 20, 14, 7, 5, 3 until the minimum that we can do. So it's called a scaling process. So bila kita nak buat scaling of the gate, so in this case you want to scale this gate, the width of the gate or the CD. Bila you scale down, then the oxide thickness, gate oxide bawah ni, the oxide has to be scaled accordingly. Maknanya dia kena follow to some extent, dia akan reduce. So maksudnya if you are say if you're fabricating a 10 micron gate width, so you probably can use a gate ox of perhaps, I don't know, 10 nano, 20 nano, 30 nano, 40 nano. On the other hand, if you go down to 7 nanometers, so you might need to reduce the thickness of your gate ox as well to somewhere below 3 nanometers to be able to be scaled accordingly, right? So below you scale, when we do the scaling of the gate, so that means the whole thing, source, drain, body, gate ox will be scaled accordingly. If you move down to 10 micron to 10 nano, the whole thing will be scaled down accordingly. So bila you scale down accordingly, maksudnya you can pack many more transistors on the same area of the wafers. So maksudnya then we can pack more. Bila we can pack more transistors, then satu chip yang you ada tu can do more jobs. So that's why sekarang kalau you tengok phone and laptops, it can do more stuff. It can do AI, it can read your whatever, it can be bionic. Macam A12 punya iPhone A12 bionic chip, it can pack modems and whatever. It can do more stuff, it can do more functions. So these can only be realized by packing more transistors into the same area of the wafer. So maksudnya kita hanya boleh dapat benda tu dengan scaling lah. The moment you reduce everything accordingly, then you can pack more stuff into the same area, doing more jobs. Then we can enjoy the benefits of getting to do more things with our phones. Sekarang phone kan dah ada AI and adjustment and macam-macam kan. It can do all the magical stuff that we've never imagined 5-10 years ago. So this is due to the scaling of the chips in the device. Okay, so maksudnya apa yang kita belajar ni is actually what you are enjoying nowadays. So if you're having Huawei or iPhone, whatever, you can see apa features yang you ada dalam phone yang tak ada pada phone lain, and that is due to the scaling of the chips yang kita tengah belajar sekarang. So what we're learning now is actually in your pocket, right? You can see your phone like never before. Okay, so the moment you scale the whole thing down, the gate ox has to be scaled down as well. So the same goes to source and drain and body as well. So bila kita nak scale down, kita akan device ni, CMOS ni, dia akan ada new issues yang we've never seen before due to the scaling problem, right? So to be able to address this problem, so one issue that we have to address is that we have to use a high K dielectric. High K itu apa? So high K dielectric is actually referring to this gate ox only, ya. Kita tak cakap tentang gate, kita tak cakap tentang source, we're not talking about drain, not even the body. We are only talking about the gate ox now. So it's only on the gate oxide, gate ox. So material with a high K, high dielectric constant, or K, or kappa, is needed when we scale the whole CMOS to a smaller size. So kenapa kita perlu high K? Let us go through this. So used in semiconductor manufacturing or wafer fab processes to replace SiO2 gate dielectric with another dielectric layer. So all this while when we fabricate CMOS in the fab, so fab has been using SiO2 gate ox. So gate ox ini is based on SiO2 all this while. Okay, so this may no longer be the case due to certain issues. Okay, so kenapa? So as one of the several strategies developed to allow further miniaturization of microelectronic components. So this is actually the scaling that I was talking about now. So kalau kita nak, have you ever heard about Moore's law? Okay, Moore's law ni, it's not a law per se. Dia bukan macam Newton's law or some other physics law. It's not a law per se, but rather it's an observation made by Gordon Moore. Who is this Gordon Moore? Gordon Moore is one of the founders of Intel back in 1965. So this law is actually not a law yang legit law lah, maksudnya is rather an observation, pemerhatian. So Mohd ni cakap, dia kata when based on his observation since 1965 until years after that, dia nampak the transistor density in the chip, the density of transistors always double every 2 years. So maksudnya from 1970s to 72 the transistor doubles, 72 74 doubles. So every 2 years, and in fact some other statement says that he also said that the transistor density doubles every 18 months, 1.5 year or 2 years or so. Okay, so bila kita buat scaling ni, to be able to allow the scaling to happen, kita kena to be able to extend the Mohs law, maksudnya to be able to keep seeing the doubling of transistor density per unit area forever. Kalau kita nak nampak effect tu sentiasa, then you have to do the scaling. Barulah you can realize the doubling of the transistor every 18 months or every 2 years. Okay, so maksudnya the moment ada observation ni and it's made official more or less, so company dalam industri they try to meet the Mohs law punya forecast. So maksudnya they are driving themselves to always deliver the doubling of transistor density every 18 months or every 2 years. So maksudnya semua pun drive lah, let's do together, let's make sure that the Mohs law can be extended. So that's why bila you tengok dalam teknologi node tadi kan, so it has been driven down from microns until now around 7 or 5 nanometers. So this is due to the law made or published in 1965, and then people came in together to drive initiatives to make sure that the doubling of transistor can be realized. Okay, so then maksudnya you have to do the scaling to be able to extend the law forever, but it couldn't go forever sebab you are limited. Kalau you are pushing down the gate up to certain extent, how much can you push? Theoretically, how much can you push? What do you think? Kalau nak kecilkan size gate and in transistor size, how low can you go? What do you think? What's the limit? What's the fundamental limit? How small can we go? Remember, we use silicon in this case for our chips nowadays. How small can we go? The smallest we can go is the size of a silicon atom. So you can push, you can scale down the whole thing. Tapi bila sampai dekat size satu silicon atom, then that's it. That's the fundamental limit. This is the size of silicon atom. Nanti you balik, you check what's the size of silicon atom. So that will be the smallest gate possible. If you want to stick to CMOS architecture. If you want to move to another architecture, then that's a different story. Okay, but that's the fundamental limit of CMOS. So why then do we need high K? So SiO2 has been used for decades. As MOSFET decrease in size or CMOS decrease in size, SiO2 thickness steadily decreases as well. So as I said now, it was probably 10 nano or 30 nano back then, and now it has been reduced to, if you look at this TEM image down here, so need TEM, transmission electron microscope, is much more advanced than an SEM. It's much advanced than scanning electron microscope. So tengok kat gate ni kat atas, ni cross section gate kat atas. Thickness of SiO2 is only 1.2 nano. So bawah ni silicon. So cross section of a CMOS. So gate ox silicon is a very thin layer of oxide, 1.2 nano only. It's like 3 or 4 layers of SiO2. Kalau you check SiO2 punya single layer, then you can see perhaps it's somewhere around 3 or 4 layers of SiO2. Then if you scale down the whole device accordingly, maksudnya the minimum you can go is actually a single layer of SiO2, right? So that will perhaps be 0.4 or 0.3 nano for a single layer. So SiO2 thickness steadily decreased to increase gate capacitance. What is gate capacitance? Still remember what is a capacitance? Nanti you kena tengok dekat video yang saya bagi. So remember a basic representation of a metal plate. parallel plate capacitor. You have a conductor here, you have a conductor here, you have insulator in between. So this is actually the same thing. So we have a gate here, we have a semiconductor down here, and our gate aux is in between. So sama konsep dia, gate aux kat tengah ni. So it's just a parallel plate capacitor in a miniaturized version. Okay, so we have to increase the gate capacitance in a small device so that we can improve the drive current in a CMOS, thereby we can improve the performance. So maksudnya the aim of the scaling is to increase performance so that you can do more things, you can go for faster speed. Maksudnya nanti you boleh increase the laptop punya switching speed to higher gigahertz. Sekarang kita perhaps around 2 something. Dah ada 3 point something gigahertz laptop punya processor. Do you have 3 point something already or still at 2 something? I think the consumer electronics perhaps are around 2 something gigahertz. Kalau you nak increase that, then you have to do this. You have to scale down, you have to increase gate capacitance, you have to increase the drive current, therefore increasing the performance, right? Thickness, the moment you go to below 2 nanometer thickness for SiO2 gate aux, then there will be leakage current due to tunneling effect. So kita dah belajar sebelum ni kan, kalau if it's too thin, if it's too near, then we're gonna have tunneling effect drastically. So maksudnya if you have tunneling, then your oxide will no longer serve as an insulator. So maksudnya kalau you tengok kat parallel plate punya konsep ni, ruang ni dia boleh dah, current boleh just penetrate. So due to leakage, right? Because it's too thin, leading to high power consumption in the device and reduce device reliability. So maksudnya kalau kita nak switch on 0, then it might end up as still 1. Kalau you nak device tengah on, you nak turn it off, so it might still be on or the other way around. Okay, so switching will not be successful and efficient anymore due to leakage. So kalau you nak turn it off, then maybe it will still be on because of leakage, right? So replacing SiO2 gate dielectric with a high K material allows increase of gate capacitance without associated leakage. Maksudnya, the moment you go thinner, then we will suffer from leakage current. Sekarang kita nak go thin, but we don't want to suffer from leakage current. Then, that's the reason of high K dielectric punya requirement. So we need to have a high K dielectric material to replace the silicon oxide. So on this slide, gate aux in a MOSFET or in a CMOS can be modeled as a parallel plate capacitor, just like I drew just now. So ignoring quantum mechanical and depletion effect from silicon and gate, kalau you ignore the tunneling effect and so on, the basic of gate capacitance can be represented as C is equal to kappa K epsilon naught, permittivity of free space, times A. A here is the width and the length of width times length of an area transistor. So maksudnya kalau width you kat sini, length you kat sana, so the whole thing will be A. Okay, A over T. T here is the oxide thickness, T aux, right? T aux. So maksudnya, if you look at this equation, how do we increase gate capacitance? Sekarang kita punya goal is to increase gate capacitance, so then we can increase the drive current, so then we can increase the gate performance, the transistor performance. So how do we increase gate capacitance here? Macam mana kita nak increase? Lower thickness of gate oxide. You lower the thickness of gate oxide, or you increase the K, the kappa. Maksudnya high K dielectric lah. So either you reduce the thickness of T aux or you increase the value of K. Right, so that's why we need to go for high K dielectric to be able to increase the gate capacitance, and maybe we can tolerate a little bit more on the gate aux thickness so that we can maintain the device performance. In fact, we can improve the device performance. Okay. Leakage limitation constraints further reduction of T here is T aux, right? Kalau you boleh increase the K value and you can reduce the T aux thickness, so your capacitance will even increase higher than expected, right? Alternative method to increase gate capacitance is alter K value by replacing K by replacing SiO2 with a high K dielectric material. K of SiO2 is 3.9. So maksudnya if you want to go for high K, you have to go for higher than 3.9 to be able to increase gate capacitance. Alright. To reduce leakage current flowing through the structure as well as improving gate dielectric reliability. So you want your on to be on and off to be off. You don't want your off to still be on due to leakage current. Okay. So candidates for high K dielectric. Now, scientists and fabs are evaluating hafnium silicate, zirconium, hafnium dioxide, zirconium dioxide, typically deposited using atomic layer deposition. We'll see why. So if you see the periodic table, all this while, bila saya laju sikit sebab sekarang 10:47, all this while we have been discussing in this topic, in this subject, in this course, in fact, we've been discussing only about this region, right? Periodic table ada banyak lagi. Kita hanya fokus discussion kita on silicon, on phosphorus, on boron, maybe aluminium, on the metals, mainly on these areas. Okay, some maybe adalah 3,5 and so on, gallium arsenide, gallium nitride, indium phosphide and stuff. But the answers to the high K dielectric lies in the transition metal region, in the central region here. So if you look at the curve on the right hand side, it's a band gap against dielectric constant. So here is kappa K value, here is the Eg. Right. To be able to be a good insulator, energy band gap kena rendah ke kena tinggi? To be able to be a good insulator, the Eg has to be low or high? High, right? So you want it to be high. You don't want it to be 0.7. In fact, there is no insulator like that. It's not 0.7, 1.1, 2. Insulators are all higher up here, beyond 4. You tengok silicon dioxide kat mana yang kita nak guna sekarang? It's very high. It's very high. Right? But the value of SiO2 is very low. Somewhere 5 or less. I think it's around 3.9. So to be able to move to high K dielectric, we have to go towards the right hand side. So there comes all the transition elements: hafnium, silicate, hafnium oxide, lanthanum, strontium, tantalum, barium, yttrium, whatever. So all the stuff that you can see in the central region. Okay, these are among the candidates for high K dielectrics. So in fact, K is not the only requirement. There are many other requirements. There are 3 or 4 requirements. I think those requirements are in the videos that I forwarded to you on eLearn. It has to be thermally stable as well. It has to stand higher temperature. So one of the reasons because SiO2 was chosen, and in fact is still chosen until now, is due to its thermal stability. It can stand high temperature. It doesn't deform. It doesn't degrade. And K is not too bad, and it has all the other requirements. Cumanya the K value cannot be used for advanced devices, but it's not high enough and it will suffer from more and more leakage. So to be able to reduce the effects, you kena tengok balik yang equation tadi, C equal to kappa epsilon A over D tu. So one of the requirement is this. Okay, so transition elements. And the final one, CMOS gate capacitance on the drive current. So this is the drive current punya what you call equation. So drive current ID, drain current, is also called drive current. For a MOSFET can be rewritten as this: ID is equal to W over L, width over length, mu mobility of the carrier, C is the capacitance density of the gate aux. So VG is the gate voltage, the thermal threshold voltage is the TH, and then so we can see here that the ID is proportional to the C, right? ID is proportional to C. So if you want to increase the drive current, which is what we want to get in our CMOS, we have to increase the capacitance. So to increase the capacitance, you have to go back to this equation. So over T or D lah sama. So either you reduce T, thickness of the gate ox, which is already too small now. For silicon dioxide, is already 1.2, a couple of layers only. So and already suffering from leakage, or increase the K value or kappa value, dielectric constant. Then you can maintain or increase the capacitance, and therefore you increase the drive current, therefore you increase the performance of the MOS. Yep. Yes, that's it for CMOS. Done. MOSFET and CMOS. Is it clear so far? So many scribbles. Is it clear? All right. Any questions for MOSFET and CMOS? All good. All right then. So we have finished. Actually all of the topics in our course. Okay. This Monday, I'm gonna forward to you few exam questions on Elan. Then try to look at it and try to do it as well. And we'll do some of those. We'll discuss some of those in our Monday's lecture. Next week Monday's lecture. Then on Wednesday you're gonna have your test 2. So there's no class. Macam hari tu juga. You just click your attendance as normal. Macam ada class. So you're gonna be given 24 hours and exactly just like last time. And we're gonna continue back on Thursday. We're gonna do a bit of review class. Untuk recap what we've learned so far and see and connect back to the learning outcomes of the course. And minggu depan, minggu berapa? Sekarang minggu now 16, right? Minggu depan is 17, and then we are done already. And then I'm going to give you your marks for your test 1, for your test 2, but I'll keep the presentation marks for myself. Okay, so that means you're going to have your assignment 1, test 2. So they're all together 60 marks. So you're going to know your 60% more or less, right? So the remaining 40% remains as secret. Sebab we are not allowed to release all the marks to you. Sebab sekarang kita dah convert into what you call coursework mode. Tak ada exam punya ni kan. There's no more exam. And that's it. We're going to be done by week 17. Right? Any other question? Related to the test, anything? Presentation 2, any questions? Ada kira-kira tak test? Tak ada kira-kira. Tak ada kira-kira, but you might have to what you call, to comment something on the magnitude. Kalau kecil apa, kalau besar macam mana, something like that. It's analytical kind of question. Alright? Anything on test, anything on presentation 2? Tak ada Alright then, kalau tak ada, that's it for today. Thank you very much. Assalamualaikum and bye-bye and stay safe. Petang ni jangan lupa dengar Perdana Menteri punya pengumuman on financial injection. I think it's going to be on the extension or no extension of CMCO as well. So we'll see. Bye-bye. Assalamualaikum.